You are being watched right now, not by a person, not by a camera, by light itself. And somehow, that light is behaving differently because of it. Shine a beam through two narrow slits and walk away, and it acts like a wave, spreading and overlapping and painting stripes on the wall behind it. Turn around, place a detector at those same two slits so you can see which one it passes through, and the stripes vanish. The light starts acting like a stream of tiny bullets instead. Nothing touched it, nothing blocked it. You just decided to look, and it changed. That sentence alone has launched 1,000 bad YouTube videos claiming your mind bends reality, that consciousness controls the universe, that you are secretly a wizard every time you open your eyes. None of that is true, but the real explanation is stranger, better documented, and far more unsettling than the myth, because it was proven in a lab, verified by multiple independent teams, and it still makes physicists uncomfortable, more than a century after the first version of this experiment was run. Today, we're going inside that experiment. We are going to show you exactly why light changes when you look at it, who discovered it, who tried to disprove it, and why the real answer has nothing to do with magic, and everything to do with the strange machinery running underneath everything you've ever seen. Let's start with the man who broke the story wide open in 1801, an English polymath named Thomas Young. At the time, the scientific establishment had a settled answer for what light was. Isaac Newton, arguably the most influential physicist who had ever lived, insisted light was made of particles, tiny corpuscles fired in straight lines, bouncing off mirrors like billiard balls. Newton's authority was so total that for almost a century, few scientists dared challenge him publicly. Young did anyway. He built a simple setup, a single source of light, a barrier with two narrow slits cut into it, and a screen behind to catch whatever came through. If Newton was right, you'd expect two bright bands on the screen, one for each slit, like two beams of bullets landing in two piles. That is not what Young saw. Instead, he saw a repeating pattern of bright and dark bands, more than two, spread across the whole screen. That pattern is called interference, and it only happens with waves. Drop two stones in a pond and watch the ripples cross. Where two crests meet, the water rises higher. Where a crest meets a trough, the water flattens out. Young's light was doing exactly that. It was interfering with itself, like a wave. Newton's particle model couldn't explain it. The wave model could. Think about how much nerve that took. Young wasn't some outsider looking to make a name for himself by attacking a legend. He was already respected, a physician, a linguist, one of the first scholars to make real progress decoding Egyptian hieroglyphs decades before the Rosetta Stone was fully translated. He had a reputation to protect, and he spent it challenging the most trusted physicist in history, in public, with nothing but a candle, a card with two slits cut into it, and a screen. It worked. The scientific community, slowly and reluctantly, came around. By the time Young died in 1829, the wave theory of light was the accepted standard. For the next 100 years, that settled it. Light was a wave. Case closed. Except it wasn't closed. In 1905, the same year he published his theory of relativity, Albert Einstein looked at a completely different phenomenon, something called the photoelectric effect, where shining light on certain metals knocks electrons loose from their surface, and found something the wave model of light could not explain. If light were purely a wave, then a dim light and a bright light of the same color should behave the same way, just weaker or stronger. But that's not what happened. Below a certain frequency of light, no amount of brightness knocked a single electron loose. Above that frequency, even a dim light knocked electrons out instantly. That behavior only made sense if light arrived in discrete packets, indivisible units of energy that we now call photons. Each photon either had enough energy to knock an electron free, or it didn't, no matter how many photons you threw at the metal. Einstein had just reintroduced the particle. And he won the Nobel Prize for it, not for relativity, which is the theory most people associate with his name, but for proving light comes in particles. Here's a detail most retellings skip entirely. American physicist Robert Millikan spent nearly a decade trying to prove Einstein wrong. Millikan didn't like the photon idea. It seemed too radical, too much of a retreat back toward Newton's old corpuscles that everyone thought had been buried for good. He built increasingly precise versions of the photoelectric experiment, specifically to find the flaw in Einstein's math. Year after year, the data kept agreeing with Einstein instead. By 1916, Millikan published results confirming Einstein's equation to a remarkable degree of accuracy, effectively handing his own rival the experimental proof needed to win the Nobel Prize. Millikan later won his own Nobel Prize, in part for that very confirmation, a scientist immortalized for accidentally proving the theory he set out to destroy. So which was it? A wave, like Young proved, or a particle, like Einstein proved? Here's where I want you to actually stop and guess, because most people get this wrong on the first try. Is the answer that scientists eventually figured out which one was correct and the other one was wrong? Or is there a third option nobody expected? Hold that guess, because the real answer is the third option, and it's the one that makes this whole mystery so much bigger than either Young or Einstein ever intended. The resolution came from a French physicist named Louis de Broglie in 1924. In his doctoral thesis, a thesis so unusual that his examiners weren't sure whether to pass it, until Einstein himself was consulted and confirmed the idea was worth taking seriously, de Broglie proposed something audacious. If light, long assumed to be a pure wave, could behave like a particle, then perhaps particles of matter, like electrons, long assumed to be solid little objects, could behave like waves too. He worked out a precise formula linking a particle's momentum to a wavelength. It sounded absurd until experiments confirmed electrons really did diffract and interfere exactly like waves, with exactly the wavelength de Broglie's formula predicted. That single thesis reframed the entire question. It wasn't just light living a double life, it was matter itself. De Broglie won his own Nobel Prize for it a few years later, and his idea was formalized by the Danish physicist Niels Bohr into something called the principle of complementarity. The idea is this: light is not a wave that sometimes acts like a particle, and it's not a particle that sometimes acts like a wave. Light is something else entirely, something our everyday language doesn't have a word for, and depending on how you choose to measure it, it will show you either its wave phase or its particle phase. Never both at once. Never neither. You get to choose which experiment you run, but you don't get to choose what you find once you've committed to that experiment. This wasn't philosophy, it was math, and it was about to get tested in the most literal way physically possible. Richard Feynman, one of the most respected physicists of the 20th century, and a man who won his own Nobel Prize for reshaping quantum theory, spent an entire chapter of his famous physics lectures on exactly this experiment. He described the double-slit result as the single phenomenon that contains the whole mystery of quantum mechanics. The one experiment that, if you could truly explain it, would mean you understood everything strange about how the universe works at small scales. He wasn't exaggerating for effect. Decades later, physicists still open textbooks with this exact experiment for exactly that reason. Here's the escalation, and this is where the story stops being about light in general and starts being about you, specifically, standing at those two slits. In 1974, and then far more convincingly in 1989, physicist Akira Tonomura and his team ran Young's exact experiment again, but this time they didn't send a beam of light or a stream of electrons through the slits all at once. They sent them through one at a time. A single electron, then a pause, then another single electron, one by one, spaced out enough that only one particle could possibly be in the apparatus at any given moment. There was no way for one electron to interfere with another, because there was never more than one electron present. Logically, you'd expect each one to land as a single dot behind whichever slit it happened to pass through, building up two piles over time, just like Newton's corpuscles. Instead, dot by dot, an interference pattern emerged. The exact same stripe pattern Young saw with a full wave of light in 1801. Except now it was being built up one lonely particle at a time, as if each individual electron were somehow interfering with itself, as if it went through both slits at once and crossed paths with its own other half. That should be impossible. And it gets worse or better, depending on how much you enjoy having your assumptions dismantled. Physicists ask the obvious next question. Fine, if each electron is somehow going through both slits, what happens if we just watch it do that? What if we put a detector at each slit, so we can record in real time which slit each electron actually travels through? The moment they did that, the moment a detector recorded which path information for even a single particle, the interference pattern collapsed. Instantly, the dots stopped forming stripes and started forming two simple piles, exactly like Newton would have predicted for particles. Not gradually, not partially. The instant you gained the information about which slit the electron used, the wave behavior disappeared completely, for every single particle in the run from that point forward. And before you assume this is somehow a quirk unique to tiny particles like electrons and photons, consider what physicist Anton Zeilinger's team did in 1999. They didn't fire electrons through the slits. They fired Buckminster fullerene molecules, soccer ball-shaped clusters of 60 carbon atoms each, roughly a nanometer wide, genuinely large by the standards of particle physics, with a mass thousands of times greater than a single electron. These molecules still produced an interference pattern. They still behaved like waves, spreading and overlapping right up until something recorded which path they took. Since then, similar experiments have pushed the size limit even further, using molecules with hundreds of atoms. Nobody has yet found a hard boundary where wave behavior definitely stops and pure particle behavior definitely starts. The mystery doesn't shrink as the object gets bigger. It just gets more difficult to isolate from an overwhelming environment that keeps recording which path information anyway, which is, incidentally, the real reason you and I don't casually diffract through doorways on our way to the kitchen. This is the observer effect, and I need to correct something right now before it takes root in your head, because this is the exact point where good science turns into bad mysticism online. The particle did not change because a conscious mind became aware of it. It did not respond to being seen the way you or I understand seeing. What actually changed was that the detector had to interact with the electron to register which path it took, bouncing a photon off it or otherwise physically coupling to it. And that interaction is what destroyed the delicate overlapping wave states that produce interference. Physicists call this decoherence. Any interaction with the surrounding environment that could, even in principle, record which path information is enough to collapse the pattern, whether a human being ever looks at the data or not. You could run the entire experiment, record which slit every electron passed through onto a hard drive, delete the file without anyone ever reading it, and the interference pattern would still be gone. Consciousness has nothing to do with it, information does. If it becomes possible anywhere in the universe for something to know which path a particle took, the particle stops behaving like a wave. That's the real mechanism, and honestly, it's stranger than the myth, not weaker than it. I want to address this directly because this is exactly the kind of result that gets hijacked. You've probably encountered claims online, in self-help videos, in documentaries with far less rigor than the one you're watching right now, that quantum physics proves your thoughts shape reality, that focused intention can bend outcomes, that consciousness is somehow the fundamental ingredient of the universe. None of that follows from what we just showed you. The equations don't require a mind, they don't require awareness. They require a physical interaction capable of storing which path information, a detector, a stray photon bouncing off a particle, a single atom nudged out of place. A camera left running with nobody in the room produces the exact same collapse as a room full of physicists staring intently at a monitor. The universe doesn't care whether you're paying attention. It cares whether the information exists somewhere, in some physical form, even briefly. That distinction is the entire difference between real, testable, Nobel-winning physics and the version of this story that sells self-help books. Now here's the part that even most physics documentaries leave out, and it's the part that should genuinely unsettle you. In 1978, physicist John Wheeler proposed a thought experiment that seemed too strange to actually build. What if you waited until after the particle had already passed through the slits, after it had, in some sense, already decided whether to behave as a wave or a particle, and only then chose whether to measure which path it took? Could you retroactively force a particle to have behaved like a particle the whole time, even though moments earlier it appeared to be interfering with itself like a wave? Wheeler called it the delayed choice experiment, and for decades it stayed theoretical. Then, in the year 2000, a team led by physicist Yoon Ho Kim actually built it, using pairs of entangled photons and a clever optical setup that let them choose, after the fact, whether to erase the which path information for one photon based on measurements of its entangled partner. The result matched Wheeler's prediction. Later, in 2007, physicist Vincent Schack and his team ran an even cleaner version of the same test, using fast optical switches to make the choice of what to measure genuinely random and genuinely delayed until after the photon had already passed the point where a wave or particle decision should have already been locked in. Both experiments confirmed it. The pattern you get depends on a choice made after the photon has already gone through, as if the photon's past behavior isn't fixed until the information about it either exists or is erased. Here's how the mechanics actually work, stripped down to the essentials, because the setup is clever enough to deserve a clear explanation instead of just a wow factor summary. Each photon sent through the slits has an entangled partner photon, generated at the same instant, linked to it in a way that measuring one immediately tells you something definite about the other. Instead of putting a detector directly at the two slits, the experimenters let the original photon travel onto the screen, while its entangled partner is sent down a separate path, one considerably longer, one that reaches a set of mirrors and beam splitters only after the first photon has already hit the screen and been recorded. At that second, later station, the experimenters make a random choice. Either measure the partner photon in a way that would reveal which slit the original photon used, or measure it in a way that erases that information entirely. When they choose to erase it, going back and sorting the already recorded data on the screen by which choice was made later, the interference pattern reappears in the data, even though the original photon already hit the screen before that choice was ever made. When they choose to preserve the which path information instead, the pattern disappears from that same sorted data. The screen was hit first, the choice came after, and the choice still determined what kind of pattern the earlier data showed. I know how that sounds, so let's guess together for a second. Does this mean the photon can send a signal backward in time, letting you change the past? No, and this is an important, evidence-backed correction, not a cop-out. You can only see the interference pattern reappear after you've compared it against the later measurement of the entangled partner, which means the information about which choice was made still has to travel to you at or below the speed of light before the pattern makes sense. Nothing here lets you send a message into the past or influence an event before it happens. What it does show is that the neat, everyday assumption that events must be fully decided in a fixed order, moment by moment, breaks down at this scale. The photon's story isn't finished until all the information about it, including information gathered later, is accounted for. Let that sit for a second, because I don't think words alone do it justice. This is not a rounding error in some obscure branch of physics that nobody checks anymore. This has been repeated, refined, and confirmed by separate labs on separate continents using different equipment. It is one of the most rigorously tested strange results in the history of experimental science, and it still reads like something out of a script written by someone who doesn't understand how time is supposed to work. It's worth pausing here to talk about the human cost of this discovery, because the story of quantum mechanics is not just a story of clever experiments. It's a story of brilliant people who spent their entire careers deeply uncomfortable with what their own equations were telling them. Einstein, the same man who proved light comes in particles and won a Nobel Prize for it, spent the last 3 decades of his life trying to find a flaw in quantum mechanics. He believed there had to be some hidden, deeper reality, some missing piece of information we simply hadn't discovered yet, that would restore a tidy, deterministic universe where particles have definite properties whether or not anyone measures them. He famously argued with Niels Bohr about it for years, most visibly at the Solvay conferences of the late 1920s and early 1930s, where the two men would spend entire dinners constructing elaborate thought experiments designed to expose a flaw in the other's position. Einstein would arrive with a new scenario each morning, meant to prove quantum uncertainty had to be incomplete. Bohr would stay up through the night working out why the scenario didn't actually break anything, and return with an answer by breakfast. Neither man ever fully convinced the other. Einstein never accepted that reality itself could be this uncertain at its foundation. He died in 1955, still believing there was a hidden explanation waiting to be found. In some ways, this whole video is a message to him decades late. Physicists went looking for that hidden explanation, and instead they found delayed choice experiments that make the mystery deeper, not shallower. Bohr, for his part, didn't come out of this unscathed either. Colleagues who knew him described a man who could spend days circling a single sentence in a paper, terrified of stating the implications of his own theory too casually, too confidently, in case it misled the next generation of physicists into thinking they understood something they didn't. He wasn't gloating over Einstein's discomfort, he shared a version of it. The difference was that Bohr had made peace with an uncomfortable idea, that some questions about what is really happening to a particle between measurements might not have an answer at all, not because we lack the technology to find one, but because the question itself may not apply the way it does to a baseball or a person. That's a genuinely difficult thing for a scientist to accept, built as the profession is on the assumption that better instruments eventually reveal deeper truths. Bohr spent his final years still defending that position to skeptical students, still fielding the same objections Einstein had raised decades earlier, because the mystery never fully went away, it just kept surviving every attempt to explain it away. So where does that leave us now, in a world that runs on this weirdness, whether we've made peace with it or not? This isn't locked away in a physics department somewhere, purely theoretical. The same principles behind wave-particle duality and the observer effect are the foundation of quantum computing, where information is stored not as ordinary ones and zeros, but as overlapping possibilities that only resolve when measured. The exact behavior you just watched electrons perform at those two slits. They are the foundation of quantum cryptography, where the very act of an eavesdropper trying to intercept a message physically disturbs it, alerting the sender, because observation itself changes the system, the same way that detector at the slits changed the electron. And in 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger for experiments proving that this strangeness isn't a flaw in our measuring equipment. It's a real, physical feature of the universe, tested and confirmed with particles separated by kilometers, closing every reasonable loophole skeptics had proposed for half a century. This isn't fringe science. It's Nobel-winning, repeatedly verified foundational physics. It just happens to sound like fiction. There's a quieter, less flashy application worth mentioning too, because it shows how deeply this weirdness has already worked its way into ordinary life. Modern atomic clocks, the kind that keep GPS satellites synchronized to billionths of a second, letting your phone tell you exactly where you are, rely on precisely controlling quantum states of individual atoms. States that only make sense because those atoms exist as overlapping possibilities until measured. You are not casually adjacent to this mystery. You have almost certainly used a piece of technology today that only works because engineers accepted and built around the exact behavior you just watched happen to a single electron at two slits. Medical imaging leans on the same foundation. MRI scanners work by manipulating the quantum spin states of hydrogen atoms in your body, states that, much like the electron's path through the slits, only settle into a definite value once measured. The mystery you've been watching unfold on a screen behind two slits is quietly running in hospitals, satellites, and research labs around the world, every hour of every day, whether or not anyone stops to notice how strange the underlying physics actually is. Here's the honest version of what's actually happening, stripped of every mystical add-on the internet has bolted onto it over the years. Before you measure which slit a particle goes through, it doesn't have a definite path at all. Not a hidden one we haven't found yet, but genuinely no definite path, existing instead as a spread of overlapping possibilities described by something physicists call a wave function. The moment any physical interaction anywhere records which path information, that spread collapses into one definite outcome. It's not that the particle knew it was being watched. It's that watching, in this context, always requires a physical interaction, and physical interactions are exactly what force an undefined possibility to become one defined fact. Light doesn't change because you looked at it in the way you're imagining right now. Light changes because looking at this scale is never passive. There's no such thing as observing something at the quantum level without touching it, and that single fact rewrites what the word watching even means. I'll admit something to you honestly, because this channel runs on evidence, not just entertainment, and building an episode like this one takes real time, tracking down the original Kim 2000 paper, cross-checking the Jacques 2007 replication, making sure Tonomura's 1989 results are represented accurately instead of the oversimplified version that circulates online. If this kind of deep dive, no-nonsense science reporting is worth something to you, a super thanks genuinely helps keep this research-heavy format alive, one video at a time. No pressure, but if you've made it this far, you already know this isn't the kind of video that gets made carelessly. Before you go, I want you to actually answer the question this video opened with, in the comments, honestly. Did you guess wave, particle, or something else before we got to complementarity? And here's the thread we're pulling next, because this mystery doesn't stop at wave-particle duality, it gets worse. Those entangled photon pairs we mentioned briefly, the ones used in the delayed choice experiments? Measure 1 and its partner instantly reflects that measurement, even if it's on the other side of the planet, even if there's no time for any signal to travel between them at the speed of light. Einstein called it spooky action at a distance, and he hated it even more than he hated the observer effect. Next time, we go inside the experiments that proved him wrong about that too, and we'll show you exactly how far apart two particles can be while still, somehow, acting like one. Here's a preview worth sitting with until then. In 2017, Chinese researchers used a satellite named Mischius to send entangled photon pairs to 2 ground stations more than 1,000 kilometers apart, and the correlations between measurements at each station still violated the classical limits Einstein believed had to exist, over a distance where any ordinary signal would need several milliseconds just to cross. That experiment, along with decades of ground-based tests going back to physicist John Clauser's original work in the early 1970s and Alain Aspect's landmark experiments in the 1980s, is part of exactly why Clauser, Aspect and Zeilinger shared that 2022 Nobel Prize we mentioned earlier. Each of them, working decades apart, closed a different loophole skeptics had proposed to explain the results away using ordinary physics. None of the loopholes held up. So the next question is simple, and it's the one we'll answer next. If 2 particles can be torn apart by 1,000 kilometers and still respond to each other instantly, what does that actually mean for the idea that anything in this universe is truly separate from anything else? Sit with that. We'll meet you back here tomorrow to take it apart, piece by verified piece.